第一个工作呢是基于空间划分与 GAN-GP 的使用动态安全域边界的快速生成方法。研究的团队呢是来自天津大学的团队，解读人呢是来自于我天津大学的刘艳丽老师。那我们这个期刊呢也是全英文的一个综合性期刊，所以关于第一个报告的相关工作，我会用英文为大家来介绍。So there will be three key parts. The first part, I would like to give a basic idea about what is security region. Actually, we are very familiar with the point-wise method we always use in the past time for the operation and dispatch operators in power system. That means we always check whether the operation points satisfies the power flow constraints by numerical calculation. So we just take a further stability, for example. So what is the security region methodology? So compared with the point-wise method, security region methodology, it is defined in power injection space, includes multiple stable constraints, and uniquely determined by network topology and system parameters independent of operating states. So just like the figure shows, actually we more focus about the whole region. The operating points satisfies the operation constraints. So that means we can clarify the boundary, where is the security region and what is not a security region. So about the security region is also correlated with the stability problem we are focused. So we are very familiar about the stability of power system. Actually, it can be calculated in different one. For example, integrated security region, and we also focus maybe separately focus on, for example, steady state security region, static voltage stability, and small disturbance stability, and also the dynamic security stability. So that means based on the security region methodology, we can also clarify the related security region for each stability problem. So if we focus on the crossing area, carry all stability problem, we will get the integrated security region. And this work is more focused about the practical dynamic security region of the transmission system. So before we introduce the specific work, so we should know what is practical dynamic security region. And the figure show, actually, the practical dynamic security region, it is defined the size of all operating points with an injection power space and practically defined bonds that ensure transient stability of the power system prior to large disturbances. So you can see, actually, is also correlated. I mean, the strong relationship between the functions we are really familiar with. And during the past history of research conducted by Tianjin University, actually, with about the practical dynamic security region of the transmission system, we conclude some differential topology characteristic about it. So there are three very important ones. And the first, there's no holes inside. We call it a differential topology characteristic 1. That means about dynamicity. And we can see that no holes inside the security region. So that means that follows the second one about the differential topology characteristic. That means about the boundary, it is continuity. And then compactness. So actually, these three key differential topology characteristics has already proven by the mathematical view in the past published paper also in engineering. So if you are interested, how can we conclude that? You can focus on the details in that paper. So let's move to the second part. We know what is practical dynamic security region, and now how can we obtain an even faster generation about the boundary? Actually, there are three main methods existing for this: fitting method, analytical method, and artificial intelligence and data-driven method. I can show one by one. For the fitting method, actually the basic idea is very simple. That means for a given contingency and fault clearing time, I mean the fault detail, an injection point Y is critical if the possible system remains stable and Y but becomes unstable under. That means based on the point Y's method, we check and simulate many operating points to check whether it is Q or not Q. That means we will get the boundary across the stable and unstable part, and then we simulate the boundary. So the basic idea is based on the pointwise method, and we simulate a large number of operating points, and then we got the boundary. Second method, that's analytical method. I think is very simple to understand. That means we use a mathematical way to conclude how can we obtain the practical boundary for the PDSR. However, during the past decades of research, we should simplify some conditions. Then we can get the analytical equation about this part. So that means for analytical method, maybe it's fast. However, the accuracy will be affected. And about the third method, that's very hot. Since we compared with the previous two methods, we will get the key idea. The way we generate a lot of points along the boundary, that will be the most important. So data-driven method will prod in this area. That means we establish a data-driven method, the AI method, and we use it to generate a lot of data to help us know, okay, what is the stable points and what is the unstable points, and then we use the similar way to get the boundary. If we analyze all these three typical methods, we will have the key conclusion. First of all, the key is to obtain enough points just along the boundary. And second of all, for fitting method, the accuracy is the most one. And for the analytical method, it's fast. However, the accuracy will be affected. And for the data-driven and AI-based method, if, however, we are not sure the operates, I mean the points obtained will be reliable. I list a picture in the rightest part. You can see we use the AI-driven method and maybe data-driven method. We generate a lot of sample operating points. However, what we really need is the points along the boundary, but the samples are not reliable. That means, although we obtain the boundary, it's not reliable one. So the key vision and the key idea we did about that is that we should obtain the boundary location based on the mathematical view, and then just inside a limited space, we generate the sampling points based on AI. Then we can obtain the reliable points just along the boundary. So here the work. That's the PDSR boundary generation based on space division and WGAN GP. And the key idea I mentioned that actually the efficient comprehension of critical point search space based on space division and relief feature extraction is established to help us locate where the boundary will be inside. And then, based on the AI method, the WGAN GP, we implementing critical point data augmentation to quickly obtain the critical point size. So, about this method, actually there are three key steps. The first one, we comprehending the space based on the space division and relief. That means that's the most important part. We locate the space where the boundary just inside it. And about the step 2, we use the WGAN GP method to obtain the enough data what we need, but just inside the shortened space. And about the step 3, we will fit in the boundary based on the least squares method according to the previous 2 steps, the data we obtained. So for the first step, you can see the key idea. Actually, during the operating area, we can clarify into 3 dimensions. The first, stable operating area, and second, unstable operating area, and 3, that's the most important. That means that will be the key part where the boundary just located in. And as I mentioned, during the past decades of research conducted by Tianjin University, we conclude the differential topology characteristic about the PDSR. So that means we use a mathematical way to give the real equation to describe where is the critical operating area. So the detailed equation will be given in the paper. And about this part, meanwhile, we are bringing the relief algorithm. It is a classic feature selection method proposed by Kia, so which measures the importance of features through relevance statistic. So that means based on the space division method, that's the straight equation to describe the critical area. And meanwhile, combined with relief, we can shuttle down the space to search reliable boundary points. Yeah. And step 2. So since we got the boundary located inside space, that means the critical operating area, we have already know that. So next step is how can we obtain enough sample data to help us generate the final boundary. So we bring in the WGAN GP method. It is an improved generative and visual network designed to address training instability and mode collapse in original GNs. And we improved through these packs. First, we establish the Wallenstein distance, and then we improve the objective fraction, and then we also design the loss function to design the whole network. So the details and also given in the paper. Since we have enough reliable points just along the boundary, so the final step will be the fitting boundaries. And we bring in the least squares method. So first of all, we diversion equation for critical points, and the sum of squares of diversion should be minimized. And by using the above equation, we will calculate the partial derivative, and then the least squares estimation of hyperplane coefficients can be obtained. And as I gave the introduction about the PDSR, actually, the hyperplane will be the key part to given the final boundary expression, the mathematical expression. And the total method is verified in the typical test case. We use the New England 10 machine and 39-node system and all N- contingencies. And meanwhile, we also established this test case replaced by the wind farm in one location. So here the key data, we use the method test in the New England system. We can see that if we bring in the space division method, and it will be reduce the computation time a lot. It will be by 17.84% compared to the relief method and by 57.59% compared to the fitting method. So that means although we bring in this and also using the data-driven method, the computation time is reduced. And meanwhile, we can also do the comparison between this method and also to the fitting method, and also the method only use the relief. So here also lists the comparison result. The computation time is also decreased very a lot. And meanwhile, we also do the extended test case in a larger system, and we can see the calculation time will be within 6 minutes significantly. And I think that will be another 4 minutes for me. And actually, the key idea about this part also expanded to the distribution side. So we also have the practical steady state security region. We call it PDSR. So the key idea also bringing in the distribution side. So here the step. Actually, this is not the paper content, but that's the key point to co-relationship with the transmission side, since we will do the layered security region for each part. So we can see actually we can also pre-screening of critical hyperplanes and also search of critical hyperplanes. And finally, we will how to shuttle down the hyperplanes. And we also did the comparison with the new method and also the other method we had already used. And the accuracy, efficiency is also improved. And another thing we want to strengthen, actually, during the optimization problem, we use the security region methodology. Actually, not many constraints are necessary. So the key idea we propose shuttle down the hyperplanes. I mean, we just obtain the critical hyperplanes. It can help us improve the calculation efficiency. So this is a comparison results. And especially, we also bring in the data-driven refined solution about the critical hyperplanes for the PDSR boundaries. And the key idea is also the similar. We establish the power flow mapping characteristic and help us to establish the network to obtain the final coefficients about the boundary. And this is also the key step. We establish the basic network, and then we got the characteristic of distribution network power flow mapping, and then we can self-evolving polynomial network to help us adapt to the new network and obtain the boundary very efficiently. And we also did the test case in the typical distribution network. We can also see the efficiency is very good and the results are reliable. So I think that's the key part about my introduction. And here we list the volume information. Actually today, all 5 speakers just introduced the content just in the volume 15.1. And it's published in August in 2025. And my work, you will be found. That's the cover paper of this volume. And meanwhile, we also did a lot of work, physically informed small data-driven situational awareness work. If you are interested, you can also follow the related papers especially welcome to focus the papers published in engineering. So that's my part. If you have any question, just contact me.